faithfully sharing insights and exploring great books worldwide. Hi, this is Sally with the Book Talk. Today we're diving into the book Paradox, subtitled Cracking the Nine Most Complex Mysteries in Scientific History. A paradox is a proposition that leads to two contradictory conclusions. In scientific progress, after a theory is proposed, it can sometimes yield seemingly absurd results. That's when a paradox emerges. Paradoxes fall into two types. True paradoxes, which are unsolvable. For example, which came first, the chicken or the egg? And there's another type called cognitive paradox. These paradoxes sound outrageous or counterintuitive at first, but they miss subtle factors. Once considered, the paradox resolves. This cognitive paradox is precisely what the book focuses on. These paradoxes are like the tip of the iceberg, hiding a vast knowledge system beneath. The book introduces the nine most important paradoxes in scientific history. They span over 2,000 years, covering Newtonian physics, thermodynamics, relativity, quantum physics, and more, linking physics evolution. The author, Jimma Khalili, born in Iraq, is a top physicist, professor at University of Surrey, and a renowned writer and broadcaster. He was awarded the OBE, plus the Michael Faraday Prize from the Royal Society, and the Kelvin Prize from the Institute of Physics for Science Education. Innovative, critical products, Al-Khalili breaks the norm of starting simple in popular science books. He first presents baffling paradoxes, then delves into them in a fun way, guiding us to understand the science behind the paradoxes. I'll split them into two groups to explore 7 key paradoxes. The first group is animal-themed, using 4 animal paradoxes to introduce 4 physics areas. The second is relativity-themed, focusing on 3 relativity paradoxes to delve into its wonders.
Let's kick off this mind-bending journey of solving paradoxes.
First up, the animal-themed paradoxes. In physics, scientists created 4 animals in thought experiments, representing 4 famous paradoxes. They are Zeno's tortoise, Laplace's demon, Maxwell's demon, and Schrödinger's cat. Some call them the 4 mythical beasts of physics, corresponding to calculus, classical mechanics, thermodynamics, and quantum mechanics. Witnessing physics evolution. From ancient times to now, let's explore the origins of these 4 legendary creatures. The first paradox is Zeno's tortoise paradox, also known as Achilles' paradox, dating back 2,500 years, to the Greek philosopher. Proposed by Zeno, it involves a hero from Greek mythology known for his speed. Achilles races a tortoise that gets a 100-meter head start, with Achilles chasing it. But when Achilles reaches 100 meters, the tortoise has crawled another 10 meters ahead. Achilles chases 10 more meters and the tortoise crawls 1 more meter. And Achilles chases 1 more meter and the tortoise crawls 0.1 meter further. So the tortoise always stays ahead, constantly creating distance between them. Though the gap shrinks, it never vanishes. Achilles can never catch up. Simply put, to walk from A to B, you must cover half first, but to cover half, you need to cover a quarter, then an eighth, and so on, so you never arrive. This conclusion defies reality yet seems logical. What's wrong here? Ancient Greeks lacked the concept of infinity. The paradox's flaw is that infinitely many numbers can sum to a finite value. Zeno split the distance into infinitely many parts, but adding them turns infinity into finiteness.
Half plus a quarter plus an eighth and so on seems endless, but sums to 1.
Solving this paradox paved the way for calculus. Calculus is a math toolkit invented by Newton and German mathematician Leibniz. Calculus has 2 parts, differentiation and integration, which are inverse operations. Differentiation breaks a whole into infinite microscopic parts for study. Conversely, integration combines infinite microscopic parts into a whole for study. In Zeno's tortoise paradox, Zeno only did differentiation but not integration, focusing only on a segment of the journey. He could infinitely decompose it, but failed to see that their sum is finite. So he incorrectly judged the race's outcome. This is the most intuitive solution to Zeno's tortoise paradox.
But people's discussions didn't stop there.
This paradox, over 2,000 years old, has found new answers in today's cutting-edge physics. quantum mechanics. In the paradox, Zeno divided the path infinitely. Although this approach holds in abstract mathematics, it doesn't work in physics, because once the division reaches a certain scale, quantum effects emerge, meaning microscopic particles behave completely differently from macroscopic objects. In the microscopic quantum world, particles cannot be infinitely divided. There's a smallest unit, and time and space become fuzzy at quantum scales, making precise measurement impossible.
This means Zeno's paradox is wrong from the very premise.
We've successfully solved the first paradox. Coming to 1814, the second mythical beast arrived, named Laplace's demon. Laplace was a French mathematician and physicist, once Napoleon's teacher, hailed as the Newton of France. Like Newton, Laplace was a proponent of determinism, meaning everything can be answered through physical calculations. He proposed the hypothesis of Laplace's demon. There's a mythical beast that knows the position and state of every particle in the universe at a given moment, so it can predict everything in the future based on classical mechanics laws. In other words, if Laplace's demon were a supercomputer with immense computational power and complete cosmic information, humans could use it to calculate the universe's future. But thus, the paradox arises. The future becomes predestined. From the universe to our individual lives, everything is predetermined. It's just that our computational power is limited. Even scarier, humans would have no free will, because Laplace's demon could track all neuron movements in your brain, thus predicting your thoughts, which is clearly impossible. We can resolve this paradox from both logical and practical perspectives. Logically, since Laplace's demon exists within our universe, it's part of the cosmos. Then the impact it causes during computation, like releasing heat, becomes a new factor interfering with the universe's state. If the demon includes these factors in its calculations, it generates even more interference factors. Thus, unless the demon exists outside our universe, its grasp of cosmic information is incomplete, making accurate future prediction impossible. In reality, forget predicting the universe. Even predicting a simple model is beyond human capability. In 1886, French scientist Poincaré discovered that even studying three interacting celestial bodies, Sun, Earth, Moon, couldn't yield precision. Predicting all motion patterns is impossible because tiny initial errors amplify during calculation. This is the famous three-body problem in celestial mechanics, where predicting all mathematical scenarios is impossible. The three-body problem reflects chaos theory. A tiny factor can trigger massive chain reactions. We can't even solve the three-body problem alone.
The universe has 70 sextillion known stars. Predicting it is pure fantasy.
Modern quantum mechanics completely negates future predicting possibilities. Quote, quantum uncertainty means particles can only be described probabilistically, not measured precisely, nature's microscopic law. Thus, we can never foresee the future. Which future materializes depends entirely on our present actions. Thus, Laplace's demon was eliminated. Shortly after Laplace's demon was vanquished, a new physics branch emerged mid-19th century, modern thermodynamics. In 1871, it birthed a new mythical beast, Maxwell's demon. Maxwell is considered the greatest theorist between Newton and Einstein. Einstein said, "I stand on Maxwell's shoulders." Maxwell conceived a demon, violating thermodynamics' second law. The second law of thermodynamics is one of the universe's most fundamental laws. It states that in a closed system without external energy, disorder and entropy only increase. For example, mixing cold and hot water gives you lukewarm water. It doesn't stay half cold and half hot. This level of disorder is called entropy, and reducing entropy to restore order requires energy consumption. For instance, turning lukewarm water back into cold or hot water requires energy for heating or cooling. Maxwell proposed a thought experiment, a gas-filled box with a frictionless valve. Closing the valve splits the container. A demon inside manipulates the valve to separate hot and cold atoms. For example, when a cold atom approaches from the left, The demon opens the valve to let it move right. When a hot atom comes from the left, the demon closes the valve, keeping one side cold and one hot, reversing entropy without energy since the valve is frictionless. So, this means if Maxwell's demon were built as a supercomputer that brings order from disorder without energy consumption, then humanity could create a perpetual motion machine. Modern science saw a wave of perpetual motion machine fever, with many scientists attempting development, all failing. Einstein once said, "I believe thermodynamics' second law is the only unshakable law. Some energy-consuming step must exist that we haven't discovered." Scientists battled this paradox for over a century before finding the demon-slaying sword. It's information. We'll slay the demon in 2 steps. First, since the demon separates atoms, it must first determine whether each is hot or cold, meaning it must measure atoms and extract information. This information isn't free. Information processing always carries an energy cost. In this closed, pitch-black system, an energy-free demon just staring can't distinguish hot or cold atoms, let alone separate them. Now, step 2. Treat the demon as a computer programmed to open valves. It measures atom temperature, writes a bit of data to disk, then executes commands to open or close valves based on records. Since computer storage is limited, when full, information must be deleted to free space. In physics, Landauer's principle states that erasing 1 bit of information dissipates heat energy. That's why our computers constantly generate heat. So when Maxwell's demon deletes records, it dissipates heat and increases external entropy. Thus, the demon can't reduce entropy without paying a price. It must acquire information, store it, then delete it. These information processes all require energy costs and entropy increases. Scientists finally defeated Maxwell's demon, defending thermodynamics' second law. Now to the last physics mythical beast, the renowned Schrödinger's cat. Conceived in 1935 by Schrödinger, a quantum mechanics founder, quantum mechanics has an airy principle called superposition. It means a microscopic particle can exist in multiple states simultaneously. Place a cat and radioactive atom in a sealed box. If the atom decays, it triggers poison release, killing the cat. What happens inside the box? Due to superposition, the atom could be both decayed and undecayed. Thus, the cat would be both dead and alive. Stranger still, this superposition persists until someone opens the box. Upon observation, it instantly collapses to one state, alive or dead, as if our gaze decides its fate. That act of looking resolves it. This dead-alive cat puzzled scientists for years. Solving the paradox requires explaining superposition. Why doesn't it work for the cat? Cats consist of billions of particles. Why can't they be in superposition too? Because larger, hotter objects experience greater environmental interference. What does that mean? Quantum superposition is extremely vulnerable to observation and measurement. It's not human will influencing it, but the measurement process itself that disrupts superposition. Observing an atom requires photon collisions that disturb superposition, causing collapse. In nature, photons, air particles, cosmic rays, and neutrinos constantly collide with everything, exchanging information. For a tiny atom, collision probability is low, so superposition lasts longer.
As long as it avoids particle interference, it happily stays in superposition.
But a cat is different. As mentioned earlier, larger and hotter objects experience greater environmental interference. Compared to a particle, cats are huge and warm. Long before observation, the cat undergoes countless particle collisions, collapsing superposition. Thus, we can never capture a dead and alive cat. That's all. We've covered the first paradox group. Scientists spent over 2,000 years resolving physics as 4 mythical beasts. Solving these paradoxes developed calculus, classical mechanics, thermodynamics, and quantum mechanics. You might notice relativity is missing from this physics evolution.
Now for the second paradox group, fascinating puzzles in relativity.
Einstein's 1905-1915 special and general relativity were revolutionary, so counterintuitive they became paradox breeding grounds. 3 famous paradoxes emerged. the barn pole paradox, twin paradox, and grandfather paradox. First, the barn pole paradox. To solve it, understand special relativity's length contraction effect. It means high-speed objects shorten along their direction of motion. A 10-meter spaceship might appear 5 meters long at near light speed.
Imagine a javelin and barn of equal length. An athlete runs toward it. Sensors open the rear door when the javelin fully enters.
What happens when the athlete runs near light speed? Important! No object can reach light speed. Since objects at light speed have infinite mass, we're discussing near light speeds here. Back to the barn, the athlete and a stationary observer will see completely different scenarios. To the athlete running near light speed, the barn approaches him at that velocity, so its length contracts. Thus, before the javelin fully enters, its tip slams into the rear door with a bang. But to a stationary observer, the barn is fixed while the javelin moves, near light speed, so the javelin contracts. Recall, the rear door only opens when the javelin fully enters? So the observer sees the contracted javelin enter, rear door opens automatically, and the athlete exits unimpeded. Same event. One sees collision, one doesn't. Doesn't this contradict special relativity? If unclear, check the diagram in the audiobook notes. This paradox ignores relativity's core premise. Information can't exceed light speed.
That's the key to solving it.
The front sensor must send a signal to open the rear door. To the observer, when contracted javelin fully enters, front door closes and sends signal. But by signal-send time, the javelin tip is already a full length ahead. The signal can't outrun the tip, so rear door doesn't open in time. Observer also hears the bang, resolving the contradiction. This paradox reveals a fascinating implication. Hope, length. Hopeful visionary means distances shorten at high speeds, suggesting interstellar travel possibilities. If we achieve light speed flight, could vast cosmic journeys become shorter? Absolutely. At 0.99 c light speed, 100 light years contracts to 14 light years. At 0.999% of the speed of light, that distance shrinks to just 1 light year. If reaching 0.9999% of the speed of light, a 100 light-year journey takes just 2 days, violating no physical laws. However, the cost is your time slows down. Though you experienced 2 days, a century passed on Earth. Your arrival message would reach Earth 200 years after departure. This is special relativity's time dilation effect. Motion slows time. Why does this happen? Special relativity mandates constant light speed, yet at near light speeds, surrounding light should appear slower. To preserve constant light speed, your own time must slow down. Only with slowed time do you perceive accelerated surroundings and unchanged light speed. This time dilation leads to our second paradox, the twin paradox. Imagine identical twins. One stays on Earth, the other takes a year-long, near light speed space round trip. Upon return, what age difference emerges? Earth twin sees traveler's time slow. Traveler ages 1 year, Earth twin ages 10 years. But here's the paradox. All motion is relative. From the traveler's view, Earth moves away at near light speed. Thus, Earth twin's time should slow. After 1 year away, the traveler would age 10 years. So whose time actually slowed? Who aged more? Many scientific papers claimed this refutes relativity, arguing time can't slow without contradiction. But the truth is, Earth twin aged 10 years, traveler's time slowed. Why not vice versa? The difference? The spaceship accelerates while Earth doesn't. Special relativity can't fully explain this. Special relativity only applies to inertial frames, where objects are stationary or move at constant velocity. But in the real world, there aren't many inertial frames. Accelerated motion dominates. Here's special relativity fails. That's why it's special, requiring general relativity. Earlier, we said motion slows time in special relativity. Einstein found another time-slowing method in general relativity: gravity. Stronger gravity means slower time.
Sea level clocks run slower than mountaintop clocks.
How are gravity and acceleration related?
Gravity equals acceleration, Einstein's happiest lifetime insight.
Acceleration simulates gravity. Roller coaster drops create weightlessness. Downward acceleration countering gravity. while climbing planes increase weight, upward acceleration enhancing gravity. Einstein showed gravitational space-time effects near acceleration effects, meaning acceleration slows time. Now we resolve the twin paradox. The spacefaring twin ages less because he undergoes acceleration during launch and turnaround.
Thus, spaceship and Earth aren't symmetric inertial frames.
Here gravity's time effect emerges. Near light acceleration equals stronger gravity, so the traveler's time slows, resolving the twin paradox. This paradox sparks even more fascinating discussions.
If after 1 year in space, 10 years passed on Earth, hasn't the traveler jumped 9 years into the future?
This is authentic time travel. But what if you dislike this future? Can you return to the past? This leads to the final paradox, the book's only true paradox, the grandfather paradox. Imagine killing your grandfather before he meets your grandmother. Then your father wouldn't be born, so neither would you. But if you were never born, then your grandfather couldn't have been killed. Then you would eventually be born, and once born, you would go back to the past. This argument about killing your grandfather just keeps looping in a self-contradictory circle. This is a classic time travel paradox. Can we really go back in time and kill our own grandfather? The biggest flaw in this is that it violates the law of conservation of mass and energy. If you went back 5 minutes and met your past self, then there would be two of you existing at the same time. At that moment, the universe gains an extra mass of you out of nowhere, breaking the cosmic balance. But does that mean this paradox is solved? Not yet. Over the past half-century, theoretical physics has proposed a fascinating idea: parallel universes. This idea suggests that beyond our universe, there are infinitely many coexisting and overlapping universes, each representing a possible outcome of events. With this theory, time travel suddenly becomes possible. You could go back to the past in a parallel universe, and once there, you can change the past however you want, because it's no longer your original past. Events here don't need to match your original universe. Even if you kill your grandfather in this universe, it won't prevent your birth in the original universe. The conservation of mass and energy issue can also be resolved because the energy and mass that make up you just move from one universe to another, and the total mass and energy across all universes remains unchanged. Now, the last question is, how can we actually go back in time? In general relativity, there's actually a shortcut for traversing space-time: wormholes. Wormholes are hypothetical space-time structures that are theoretically valid, first proposed by Einstein. Wormholes are like whirlpools in the sea. They form a space-time vortex that leads to a different time and place, or connects to another parallel universe. It's a potential tunnel for time travel, but neither parallel universes nor wormholes have been proven yet. Discussions about this paradox remain purely speculative. Therefore, the grandfather paradox is an unsolved true paradox, and we don't know if we'll ever find wormholes to travel to parallel universes. But if it were possible, there should definitely be future time travelers visiting our era. But so far, we've never seen them. Maybe they went to another universe. Perhaps unknown physical laws forbid time travel. Maybe they've already blended among us, keeping a low profile. This paradox leaves us with infinite room for imagination. That's the main content of this book. These paradoxes are just a few of the most famous in the river of science, and most have been satisfactorily resolved. However, unsolved puzzles like the grandfather paradox still abound in the scientific community. The author also lists 24 of the most fascinating scientific puzzles at the end of the book, categorizing them into 3 types. The first type includes puzzles that might be solved within our lifetimes. For example, whether there's an absolute limit to human lifespan and whether we'll ever be able to predict earthquakes. The second type includes questions that may not be answered within our lifetimes. For example, what shape is the universe? What existed before the Big Bang? The third type includes puzzles that even science probably can't answer. For example, did we invent mathematics to describe the universe? Or do mathematical formulas inherently exist? In inherently exist, just waiting for us to discover. These interesting questions may not all find answers, but puzzles themselves are a playground for scientists' intellectual stimulation. All right, that's all for this book on paradoxes. The reading notes are below the audio, and we'll see you next time.